Hello there and welcome to the Dreamy Science channel. I'm so glad you found your way here tonight. Perhaps you've had one of those days where your mind keeps racing. Or maybe you're simply someone who finds comfort in the gentle mysteries of deep space rather than counting sheep. Either way, you've come to the right place. There's nothing you need to do now except let your breathing slow, your muscles soften, and your thoughts drift like cosmic dust on a solar wind. Because tonight, we're traveling to our nearest galactic neighbor, the Andromeda Galaxy, a magnificent spiral of stars, gas, and quiet wonders that has been gliding through space for billions of years, slowly making its way toward us in a cosmic dance that began long before Earth even existed. We'll explore this distant island of light gently, moving from one fascinating discovery to another, learning about its ancient stars, its hidden secrets, and the beautiful collision that awaits us in the far future. Some of what you hear might surprise you, while other facts may simply wash over you like gentle waves, soothing and distant. And if these peaceful explorations of the cosmos help you unwind or give your mind a quiet place to rest, consider liking and subscribing to the channel. It helps other stargazers find their way here too, one sleepy soul at a time. Now let yourself get comfortable, and let's begin our gentle journey to Andromeda. Andromeda contains over 1 trillion stars, twice as many as our Milky Way. When you look up at the night sky on a clear evening, you might catch a glimpse of a faint, hazy patch of light in the constellation Andromeda. That gentle smudge is actually an entire galaxy, home to more than 1 trillion stars. Each point of light in that distant collection represents a sun, perhaps with its own family of planets, its own story of birth and evolution. The sheer number is almost impossible to grasp. If you could count one star every second without stopping, it would take you over 30,000 years just to count them all. But they're not just numbers. They're ancient furnaces of nuclear fire, some burning blue and hot, others glowing red and cool, all of them spinning through space in the graceful arms of their galactic home. Many of these stars have been shining for billions of years, their light traveling across the void long before life appeared on Earth. In the quiet darkness of space, Andromeda holds more stars than there are grains of sand on all the beaches of our planet. Each one a distant sun burning silently in the cosmic night. The galaxy is racing toward us at over 200,000 miles per hour. Despite the vast distance that separates us, Andromeda is not standing still. It's moving through space at an incredible speed, roughly 250,000 miles per hour, directly toward our own Milky Way. This isn't cause for alarm, though. Space is so vast and the journey so long that this cosmic approach will take billions of years to complete. The motion is steady and gentle, like a slow river flowing toward an eventual meeting. Right now, as you rest and listen, Andromeda is getting closer by about 70 miles every second. Yet even at this remarkable speed, it would take the fastest spacecraft humans have ever built millions of years to make the same journey. The galaxy drifts toward us with the patience of deep time, guided by the invisible hand of gravity across distances that dwarf human comprehension. It's a reminder that even the largest structures in the universe are in constant, graceful motion, following paths laid down by forces we're only beginning to understand. Andromeda's light takes 2.5 million years to reach your eyes. When you see that faint glow of Andromeda in the night sky, you're not seeing it as it exists today. You're seeing it as it was 2.5 million years ago, when our earliest human ancestors were just beginning to walk upright on the plains of Africa. The light that touches your retina tonight began its journey across space long before civilization, before agriculture, before written language. It traveled through the empty darkness between galaxies, patient and unchanging, carrying with it the image of ancient stars and nebulae. During its long voyage, ice ages came and went on Earth, continents shifted, and countless species rose and fell. Yet the photons continued their steady journey, unaware of the world they would eventually illuminate. In a very real sense, when you observe Andromeda, you become a time traveler, receiving messages from the deep past. The galaxy you see tonight may have changed significantly since that light departed, but its ancient glow reaches across time to connect you with a cosmos that existed long before your world took its current shape. The galaxy spans 6 times the width of the full moon in our sky. Though Andromeda appears as just a small, fuzzy patch to the naked eye, it actually covers a much larger area of the sky than most people realize. If your eyes were sensitive enough to see all of its faint outer regions, the galaxy would appear about 6 times wider than the full moon. This means that Andromeda's true extent covers roughly 3 degrees of sky, making it one of the largest apparent objects in our night sky. The reason we can only see its bright central core is that the outer spiral arms are incredibly faint. Their light spread thin across vast distances. But that hidden enormity is always there, stretching far beyond what casual observation reveals. Photography and specialized instruments can capture these extended regions, revealing the galaxy's full majesty. It's a gentle reminder that the universe often holds more than first meets the eye, that beauty and grandeur can exist in forms too subtle for our senses to detect without help. Even in its apparent smallness, Andromeda encompasses a space large enough to hold countless worlds, countless stories, countless possibilities for wonder. Ancient spiral arms have been spinning for over 10 billion years. The elegant spiral structure that defines Andromeda has been turning slowly through space for most of the universe's history. These graceful arms aren't solid objects, but rather waves of density that sweep through the galaxy's disk, triggering star formation as they pass. Like ripples on a cosmic pond, they move at their own pace, separate from the individual stars that drift in and out of them. The pattern has persisted for billions of years, maintained by gravitational forces and the galaxy's rotation. Stars born in these arms today follow the same general paths as stars that formed when the universe was young and the first heavy elements were being scattered through space. The spiral structure acts as a kind of stellar highway, guiding the formation of new suns and planetary systems in sweeping curves that stretch across hundreds of thousands of light years. It's a design both ancient and ongoing, a pattern that has remained beautiful and consistent even as individual stars have lived entire lifetimes within its embrace. The arms turn slowly, patiently, like the hands of a cosmic clock, marking time on a scale that dwarfs human experience. Andromeda has devoured dozens of smaller galaxies throughout its history. Like our own Milky Way, Andromeda has grown over billions of years by absorbing smaller galactic companions. These cosmic mergers happen gradually, over hundreds of millions of years, as gravity slowly pulls apart the smaller systems and incorporates their stars into the larger structure. Evidence of these ancient meals can still be found today in the form of stellar streams, long arcs of stars that trace the orbital paths of galaxies that no longer exist as separate entities. Some of these streams wrap around Andromeda like ghostly ribbons, preserving the memory of long-lost companions. The process isn't violent in the way we might imagine. Instead, it's a gentle gravitational dance, where stars from the smaller galaxy are gradually redistributed throughout the larger one. Each absorbed system brings its own population of stars, its own chemical history, its own contribution to the ongoing story of galactic evolution. In this way, Andromeda has become a kind of stellar museum, holding within its structure the remnants of countless smaller worlds that once drifted independently through space. The galaxy's central black hole weighs as much as 100 million suns. At the heart of Andromeda lies an object so massive and dense that it defies easy comprehension. This supermassive black hole contains the mass of roughly 100 million stars like our Sun, all compressed into a region smaller than our solar system. It sits quietly at the galaxy's center, occasionally feeding on gas and dust that venture too close, but mostly remaining dormant and invisible. The black hole's gravity helps hold the inner regions of the galaxy together, acting as a gravitational anchor around which billions of stars orbit. Despite its incredible mass, it represents only a tiny fraction of the galaxy's total weight. A reminder of just how much matter is spread throughout Andromeda's vast spiral structure. This central monster has likely been growing slowly for billions of years, accumulating mass through mergers with other black holes and the occasional consumption of nearby material. It's both the galaxy's heart and its most mysterious component, a region where the normal rules of physics bend and twist in ways we're still learning to understand. Star formation in Andromeda happens at a leisurely pace compared to younger galaxies. Unlike some galaxies that blaze with the light of rapid star formation, Andromeda creates new stars at a relatively calm, measured rate. This peaceful pace reflects the galaxy's maturity and the gradual settling of its gas and dust into stable configurations. The process happens primarily in the spiral arms, where density waves compress the interstellar medium enough to trigger gravitational collapse. But it's not a frantic rush of stellar birth. Instead, it's more like a gentle, ongoing renewal, with new stars appearing steadily over long periods. This measured approach to star formation gives the galaxy a kind of serene quality, a sense of having found its rhythm after billions of years of evolution. The stars that form today will burn for millions or billions of years, adding their light to the galaxy's glow and contributing to the slow chemical enrichment that makes planets and life possible. It's a process that speaks to the patience of cosmic time, where even the birth of suns happens with deliberate, unhurried grace. Some regions of Andromeda are completely dark, containing no visible stars. Within Andromeda's disk lie vast dark lanes, regions where dense clouds of dust and gas block the light from stars behind them. These cosmic shadows create intricate patterns throughout the galaxy, outlining the spiral structure and marking the locations of future star formation. The darkness isn't empty, though. It's filled with the raw materials of creation, hydrogen and helium mixed with heavier elements created in previous generations of stars. These dark clouds are among the coldest places in the galaxy, with temperatures often dropping to just a few degrees above absolute zero. In their frigid depths, molecules form and chemistry unfolds at an almost impossibly slow pace. Some of these regions span hundreds of light years, creating vast corridors of shadow that wind between the bright spiral arms. They represent the galaxy's potential, reservoirs of matter waiting for the right gravitational nudge to collapse and ignite into new stars. In their quiet darkness, they hold the seeds of future light, the promise of suns yet to be born and worlds yet to form. The galaxy rotates so slowly that it takes 200 million years to complete one turn. Andromeda spins through space with the stately grace of cosmic time, rotating so slowly that a complete revolution takes roughly 200 million years. This means that since the galaxy formed, it has completed only about 50 full rotations, a remarkably small number for such an ancient object. The rotation isn't uniform throughout the structure. Stars closer to the center move faster than those on the outer edges, creating the differential rotation that helps maintain the spiral pattern. At the distance where our Sun would be if it lived in Andromeda, the orbital speed would be several hundred kilometers per second, fast enough to circle Earth in just a few minutes, yet still taking millions of human lifetimes to complete one galactic orbit. This leisurely pace reflects the enormous scale of the galaxy and the vast distances its stars must travel. Even at such cosmic speeds, the journey around the galactic center is so long that entire geological eras pass during a single rotation. It's a reminder that the universe operates on timescales that stretch far beyond human experience, where even rapid motion becomes a kind of eternal, patient dance. Hidden within Andromeda's halo float, ancient globular clusters older than most stars. Scattered throughout the vast spherical region surrounding Andromeda are hundreds of globular clusters, dense balls of stars that formed when the universe was still young. These stellar cities contain some of the oldest objects in the galaxy, stars that began shining when the cosmos had barely begun to create the heavy elements we see today. Each cluster holds hundreds of thousands of stars packed into a region just a few dozen light years across, creating stellar neighborhoods so dense that if Earth lived within one, our night sky would be ablaze with thousands of stars brighter than Venus. These ancient assemblages drift slowly through Andromeda's outer reaches, following long elliptical paths that take millions of years to complete. Many formed before the galaxy's disk even existed, when Andromeda was still assembling itself from smaller fragments scattered through space. Their stars are metal-poor, containing almost none of the carbon, oxygen, or iron that make planets and life possible. They represent a simpler time in cosmic history, when the universe knew only hydrogen and helium, and the chemistry of complexity had yet to unfold. In their golden glow, these clusters carry the memory of a younger cosmos, still visible after more than 10 billion years. Vast streams of hydrogen gas connect Andromeda to its companion galaxies. Invisible to the naked eye but detectable by radio telescopes, enormous bridges of hydrogen gas stretch between Andromeda and its satellite galaxies, creating a network of cosmic connections that spans hundreds of thousands of light years. These gaseous threads are the remnants of ancient interactions, material stripped away by gravitational tides and left floating in the space between worlds. Some streams are actively flowing, carrying gas from smaller galaxies into Andromeda's outer regions, feeding the larger galaxy's continued growth. Others are more static, marking the paths of past encounters like fossil rivers in the cosmic landscape. The hydrogen in these streams glows faintly in radio wavelengths, revealing structures that would otherwise remain completely hidden from view. They show that galaxies aren't isolated islands, but part of a connected web, sharing material and influence across vast distances. These invisible rivers of gas represent a kind of galactic circulatory system, moving the raw materials of star formation from one region to another in a process that has continued for billions of years. They remind us that even in the apparent emptiness of space, connections exist, threads of matter linking distant worlds in ways we're only beginning to understand. The galaxy's outer regions contain mysterious dark matter that outweighs all visible stars. Surrounding everything we can see in Andromeda lies an enormous halo of invisible matter, a ghostly presence that reveals itself only through its gravitational effects. This dark matter extends far beyond the galaxy's visible edge, creating a spherical envelope that may stretch for millions of light years in all directions. Despite being completely invisible, it outweighs all of Andromeda's stars, gas, and dust, combined by a factor of at least 5 to 1. The dark matter doesn't shine, doesn't absorb light, and doesn't interact with ordinary matter except through gravity, making it one of the most mysterious components of the galaxy. Its presence is revealed by the way stars move in Andromeda's outer regions, orbiting faster than they should if only visible matter were present. This invisible scaffolding may have been crucial in the galaxy's formation, providing the gravitational framework around which ordinary matter could gather and condense into stars. It represents one of the deepest puzzles in astronomy, a reminder that most of the universe consists of things we cannot see or directly detect. In its silent presence, the dark matter halo holds Andromeda together, a cosmic glue that binds the galaxy without ever revealing its true nature. Some stars in Andromeda are metal-rich, formed from the ashes of previous stellar generations. Unlike the ancient globular cluster stars, many of the suns in Andromeda's disk are enriched with heavy elements, the products of countless stellar deaths that have unfolded over billions of years. These metal-rich stars formed from gas clouds that had been seeded with carbon, oxygen, silicon, and iron, elements created in the cores of massive stars and scattered through space when those stars exploded as supernovas. The presence of these heavier elements allows for the formation of rocky planets, complex chemistry, and potentially even life. Each generation of stars has added to this cosmic enrichment, gradually increasing the heavy element content of the galaxy's gas reservoirs. Stars forming today in Andromeda contain thousands of times more metals than the galaxy's first stellar generation, reflecting billions of years of chemical evolution. This enrichment process continues today as aging stars shed their outer layers and dying giants explode, adding their processed material to the interstellar medium. It's a slow but steady transformation, turning a universe that began with only hydrogen and helium into one capable of producing the chemical complexity needed for worlds like Earth. The metal-rich stars of Andromeda represent this ongoing alchemy, stellar furnaces that have transformed simple gases into the building blocks of planets and life. Andromeda's spiral arms contain star-forming regions, glowing with the light of newborn suns. Within the graceful curves of Andromeda's spiral structure lie stellar nurseries, regions where gas and dust collapse under their own gravity to form new stars. These star-forming regions glow with characteristic colors, pink from hydrogen and blue from young, hot stars that have recently ignited. The process unfolds slowly by human standards, but rapidly in cosmic terms, with individual stars taking millions of years to form, but entire clusters appearing in just a few million years. The spiral arms act as compression waves, sweeping through the galaxy's disk and triggering star formation as they pass. Behind them, they leave trails of bright blue stars, the most massive and luminous members of each new stellar generation. These hot young stars burn through their nuclear fuel quickly, living for only a few million years before exploding as supernovas. Their brief but brilliant lives illuminate the spiral structure, making it visible from great distances and giving the galaxy its characteristic appearance. In quieter regions between the arms, star formation proceeds at a gentler pace, creating longer-lived stars that will shine for billions of years. The combination creates a galaxy that is both dynamically active and peacefully enduring, constantly renewing itself while maintaining its essential structure across cosmic time. The galaxy harbors regions where time itself flows differently due to gravitational effects. In the deepest gravitational wells of Andromeda, particularly near its central black hole, and in the cores of dense star clusters, the fabric of space-time becomes curved enough to affect the flow of time itself. According to Einstein's theory of relativity, time passes more slowly in regions of strong gravity compared to areas where gravitational fields are weaker. Near Andromeda's central black hole, this effect becomes measurable, with clocks running noticeably slower than they would in the galaxy's outer regions. The difference is small but real, a few parts per million, but accumulated over millions of years. It represents a significant deviation from the time experienced in less gravitationally intense environments. This means that stars orbiting close to the galactic center literally experience less time than their counterparts in the outer spiral arms, aging slightly slower and living marginally longer lives. It's a subtle reminder that space and time are not the fixed stage we imagine them to be, but flexible, responsive aspects of reality that bend and flex in the presence of mass and energy. Even in a galaxy that appears peaceful and static, the fundamental nature of time itself varies from place to place, creating a complex temporal landscape that we're only beginning to understand. Dust grains between Andromeda's stars contain complex organic molecules. The space between stars in Andromeda isn't truly empty, but filled with microscopic dust grains, tiny particles of carbon, silicon, and other elements that formed in the atmospheres of dying stars. These cosmic dust motes are incredibly small, much finer than the smallest particles of smoke. Yet they play crucial roles in galactic chemistry and evolution. Many of these grains are coated with ices and organic compounds, complex carbon-based molecules that form in the cold depths of space. Some contain the chemical precursors to amino acids, the building blocks of proteins, while others harbor simple alcohols, aldehydes, and even sugar-like compounds. These molecules form through slow chemical reactions that unfold over millions of years, guided by ultraviolet radiation from distant stars and cosmic ray impacts. The dust grains act as tiny chemical laboratories, providing surfaces where atoms can meet and bond in the frigid vacuum of space. When these enriched particles are incorporated into new star-forming regions, they carry their complex chemistry with them, potentially seeding new planetary systems with the molecular building blocks of life. In this way, the dust of Andromeda becomes a kind of cosmic library, storing chemical information and distributing it throughout the galaxy as stars and planets form. Ancient stellar collisions have left their marks scattered throughout the galaxy's structure. Over billions of years, stars within Andromeda have occasionally encountered each other closely enough to interact gravitationally or even physically merge. These stellar encounters are rare in the galaxy's main disk, where stars are separated by vast distances, but they become more common in dense environments like globular clusters and the galactic center. When two stars collide or merge, they can create unusual objects, blue straggler stars that appear younger than their surroundings, or massive stars with peculiar chemical compositions. Some collisions completely destroy both stars, creating spectacular explosions that enrich the surrounding space with heavy elements. Others result in exotic remnants, neutron stars or black holes with unusual properties that reflect their violent birth. The gravitational waves from these ancient mergers may still be rippling through space, carrying information about events that occurred billions of years ago. Evidence of past stellar encounters can be found throughout Andromeda in the form of unusual star populations, chemical anomalies, and high-velocity stars that were flung away from their birthplaces by gravitational slingshot effects. These cosmic accidents have helped shape the galaxy's current structure, adding complexity and diversity to what might otherwise be a more uniform stellar population. The galaxy's magnetic field threads through space like invisible cosmic architecture. Permeating all of Andromeda's structure is a vast magnetic field, an invisible web of magnetic force lines that extends throughout the galaxy's disk and into its surrounding halo. This field is incredibly weak by terrestrial standards, thousands of times weaker than Earth's magnetic field, yet it plays important roles in galactic physics and evolution. The magnetic field helps regulate star formation by supporting gas clouds against gravitational collapse, and it guides the motion of charged particles, cosmic rays, that stream through space at nearly the speed of light. It also influences how gas flows within the galaxy, channeling material along field lines and affecting the spiral structure itself. The field's strength and direction vary throughout Andromeda, creating a complex, three-dimensional pattern that astronomers are still mapping and trying to understand. In some regions, the field is well-ordered and aligned with the spiral arms, while in others it becomes tangled and chaotic. This magnetic architecture is maintained by the galaxy's rotation and by the motion of charged particles within it, creating a self-sustaining system that has persisted for billions of years. Though invisible to ordinary telescopes, The magnetic field represents one of the fundamental organizing principles of galactic structure, a cosmic framework that helps shape how matter and energy flow throughout Andromeda's vast expanse. Hidden brown dwarfs drift silently through Andromeda's stellar population. Among the trillion stars that call Andromeda home are countless objects that hover on the boundary between planets and stars. Brown dwarfs that never quite achieved the mass needed to sustain nuclear fusion. These failed stars glow only with the faint heat of their formation, gradually cooling over billions of years until they become nearly invisible. They represent a hidden population within the galaxy, objects that contribute to its total mass, but emit so little light that they're almost impossible to detect from our distant vantage point. Brown dwarfs form in the same stellar nurseries as ordinary stars, condensing from collapsing gas clouds, but stopping short of igniting the nuclear fires that power true stellar burning. Instead, they settle into a long, slow fade, radiating away their internal heat over timescales that exceed the current age of the universe. Some may have planetary systems of their own, cold worlds orbiting dim brown dwarf suns in systems that receive no light from their central object. Others drift alone through space, solitary wanderers that mark the transition between the stellar and planetary regimes. Their presence reminds us that star formation is not an all-or-nothing process, but a continuum that produces objects of every size and brightness, from massive blue giants to tiny brown dwarfs that barely qualify as stars at all. Ripples from ancient galactic mergers still influence Andromeda's structure today. The galaxy we see today bears the subtle imprints of collisions and mergers that occurred billions of years ago, events so ancient that their direct effects have long since faded, but whose consequences continue to shape Andromeda's structure. These primordial encounters left behind warps in the galactic disk, asymmetries in the spiral pattern, and unusual stellar populations that don't quite fit the expected patterns of galactic evolution. Some regions contain stars with chemical compositions that suggest they formed elsewhere and were later incorporated into Andromeda through merger events. Other areas show kinematic signatures, patterns of stellar motion that reflect ancient gravitational disturbances that have been preserved across cosmic time. The galaxy's outer halo is particularly rich in these fossil remnants, containing stellar streams and shell-like structures that mark the sites of long-destroyed satellite galaxies. Even the central regions show evidence of past upheavals, with stellar populations that suggest multiple episodes of merger-induced star formation. These ancient scars have been softened by time and the galaxy's ongoing evolution, but they remain visible to careful observers, reminders that Andromeda's current serene appearance masks a violent and complex history of growth through cosmic cannibalism. Streams of escaped stars wander in the darkness between Andromeda and the Milky Way. In the vast gulf that separates our galaxy from its approaching neighbor, astronomers have discovered something unexpected: individual stars that have been ejected from their home galaxies and now drift alone through intergalactic space. These stellar exiles were likely flung away by gravitational encounters with massive objects, perhaps during close passes near central black holes or through interactions in dense star clusters. They travel at incredible speeds, fast enough to escape their galaxy's gravitational embrace entirely. becoming cosmic wanderers in the empty space between worlds. Some of these hypervelocity stars may have originated in Andromeda itself, launched on trajectories that will carry them through millions of years of lonely travel. Others might be refugees from our own Milky Way, cast out into the void by ancient stellar catastrophes. These solitary suns carry no planets, no companions, just their own nuclear fires burning steadily as they trace long arcs through the cosmic deep. Their light illuminates nothing but empty space, yet they continue their patient journey, glowing beacons in a region where no stars should exist. In their isolation, they represent one of the universe's most poignant stories, lights separated from their communities, destined to burn alone in the darkness between galaxies. The galaxy's rotation creates waves that propagate through its spiral structure like ripples on a cosmic pond. Within Andromeda's disk, density waves move at different speeds than the stars themselves, creating the spiral pattern we observe from Earth. These waves aren't made of matter, but of gravitational influence. Regions where stars and gas crowd together more densely as the wave passes through. Like up behind traffic backing a slow vehicle, material accumulates in these wave crests, triggering star formation and illuminating the spiral arms. The stars themselves drift in and out of the pattern, spending only a portion of their lives within the bright spiral structure before continuing on their individual orbits. This creates a kind of cosmic rhythm, where the spiral pattern persists even as its constituent stars flow through it like water through a riverbed. The waves move slowly by human standards, but steadily by galactic ones, completing their own orbital cycles around the galaxy's center, at rates different from the stellar population. Tie-in. This elegant mechanism allows Andromeda to maintain its spiral structure across billions of years, creating a pattern that remains beautiful and consistent even as individual components age and evolve. The spiral arms become not just static features, but dynamic phenomena, breathing with the galaxy's rotation in a slow cosmic pulse. Temperature variations across Andromeda create distinct zones where different types of stars can form. The galaxy isn't uniformly warm or cold, but contains regions with vastly different thermal environments, from scorching hot areas near active star-forming regions to frigid zones in the outer halo, where temperatures approach absolute zero. These thermal differences profoundly influence what kinds of stars and planetary systems can form in each location. In the hottest regions, near the galactic center, and within giant molecular clouds heated by massive stars, only the most robust stellar formation processes can proceed. Here, stars tend to form quickly and in large groups, creating dense clusters that shine brilliantly but briefly. In cooler regions of the galaxy, star formation proceeds more slowly and gently, allowing for the gradual accumulation of less massive stars that will burn for billions of years. The coldest zones, particularly in the outer reaches where starlight is sparse and gas densities are low, may harbor different chemistry entirely, with molecules that cannot survive in warmer environments. These temperature gradients create a kind of galactic climate system, with distinct zones that support different types of stellar and planetary formation. Over cosmic time, this thermal architecture helps determine the galaxy's overall character, influencing everything from the distribution of heavy elements to the likelihood of habitable world formation. Andromeda's gravitational influence extends far beyond its visible boundaries, affecting objects millions of light-years away. The galaxy's massive gravitational field doesn't stop at its apparent edge, but continues to influence the motion of objects throughout the local group of galaxies. This invisible reach affects the trajectories of smaller satellite galaxies, the flow of intergalactic gas, and even the large-scale structure of space in our cosmic neighborhood. The gravitational effects are subtle at great distances but persistent, creating long-range correlations that connect Andromeda to objects that appear completely separate. Some of the galaxy's satellite systems orbit at distances so vast that they take billions of years to complete a single revolution, yet they remain gravitationally bound and responsive to Andromeda's influence. This extended gravitational presence also affects the motion of our own local group, helping to determine the overall trajectory of our small cluster of galaxies as it moves through the larger cosmic web. The invisible threads of gravity that extend from Andromeda create a kind of cosmic sphere of influence, a region where the galaxy's mass makes itself felt even in the apparent emptiness of intergalactic space. These far-reaching effects remind us that galaxies aren't isolated objects, but part of a connected gravitational network that extends across the observable universe. Within Andromeda's structure lie remnants of the first stellar generations that formed when the universe was young. Hidden within the galaxy's oldest populations are stars that began shining when the cosmos was just a few billion years old. Ancient suns that have witnessed nearly the entire history of galactic evolution. These primordial stars formed from gas that contained almost no heavy elements, just the hydrogen and helium created in the Big Bang itself. Their atmospheres preserve the chemical signatures of that simpler time, providing direct evidence of conditions in the early universe. Some of these ancient giants have since evolved into white dwarfs or neutron stars, compact remnants that continue to orbit within Andromeda's structure like cosmic fossils. Others, smaller and longer-lived, continue to burn steadily, their nuclear fires sustained by the same processes that began billions of years ago. These stellar elders have watched the galaxy transform around them, seen countless generations of stars form and die, witnessed the slow chemical enrichment that made complex planets possible. Their light carries information from a time when galaxies were still assembling, when the first heavy elements were being created and distributed through space. In studying these ancient stars, astronomers can peer back through time, using their properties to reconstruct the conditions that existed when Andromeda was young and the universe was still learning how to make the elements of complexity. Vast cavities carved by ancient supernovas create bubble-like structures throughout the galaxy's disk. Scattered through Andromeda's spiral arms are enormous hollow regions, cosmic bubbles blown by the explosive deaths of massive stars millions of years ago. These supernova remnants have expanded over time, sweeping up surrounding gas and dust to create vast, low-density cavities that can span hundreds of light-years. The hot, rarefied gas within these bubbles glows faintly in X-ray wavelengths, creating ghostly structures that mark the sites of ancient stellar catastrophes. Some bubbles have merged with others, forming even larger cavities that create complex networks of interconnected voids. These structures play important roles in galactic ecology, providing pathways for hot gas to escape from the disk into the surrounding halo, and creating regions where new star formation is suppressed. The bubble walls, where swept-up material accumulates, can become sites of triggered star formation, creating secondary generations of stars born from the compressed debris of their predecessors' deaths. Over millions of years, these cavities slowly fill in as new material flows into them, but their effects on the local environment persist much longer. They represent one way that stellar death influences galactic structure, creating lasting changes that ripple through the galaxy's evolution long after the original explosion has faded from view. The galaxy harbors populations of stars with unusual chemical fingerprints that tell stories of cosmic migration. Among Andromeda's stellar citizens are groups with chemical compositions that don't match their current locations, suggesting they formed elsewhere and were later moved by galactic processes. Some contain unusually high concentrations of certain elements, signatures that point to formation in environments very different from where they now reside. Others show deficiencies in expected elements, indicating they may have formed in regions with different star formation histories. These chemical peculiarities act like stellar DNA, preserving information about the star's origins and the journeys that brought them to their current positions. Some of these unusual populations may be refugees from satellite galaxies that were disrupted and absorbed into Andromeda's structure. Others might have migrated from the galaxy's outer regions through gravitational interactions or secular evolution processes. The chemical diversity within Andromeda's stellar population creates a kind of archaeological record, preserving evidence of the galaxy's complex assembly history. By studying these chemical signatures, astronomers can trace the flow of material through the galaxy over billions of years, reconstructing the merger events and internal processes that have shaped Andromeda's current structure. Each unusual chemical fingerprint represents a piece of galactic history, a clue to understanding how this magnificent spiral assembled itself from smaller components scattered across space. Invisible rivers of dark matter flow through Andromeda's structure like a hidden circulatory system. Beyond the visible stars and gas lies a vast network of dark matter streams, invisible currents that thread through the galaxy's structure and connect it to the larger cosmic web. These dark flows carry no light and emit no radiation, yet they represent the majority of the galaxy's mass and play crucial roles in its evolution. The streams follow complex three-dimensional paths, guided by gravitational forces and the galaxy's rotation, creating a hidden architecture that underlies everything we can see. Some of these dark matter rivers bring fresh material into the galaxy from the surrounding cosmic web, feeding Andromeda's continued growth and evolution. Others redistribute mass within the galactic structure, affecting the distribution of stars and gas in subtle but important ways. The flow patterns change slowly over cosmic time as the galaxy's gravitational field evolves, and external influences alter the trajectories of incoming material. These invisible currents create a dynamic framework that influences star formation, galactic structure, and the long-term evolution of the entire system. Though we cannot observe them directly, their effects can be inferred from the motions of visible matter and the overall gravitational behavior of the galaxy. They remind us that most of what shapes galactic evolution remains hidden from view, flowing silently through space in patterns we're only beginning to understand. Stellar nurseries within Andromeda contain protostars that may never successfully ignite. Not every attempt at star formation leads to a shining success. Within the galaxy's star-forming regions, astronomers have identified numerous protostellar objects that appear to be stalled in their development, cosmic failures that accumulated some mass but never quite reached the threshold needed for sustained nuclear fusion. These failed stars, ranging from brown dwarfs to even smaller objects, represent the galaxy's incomplete stellar births, reminders that the process of turning gas into stars is neither guaranteed nor perfectly efficient. Some of these objects continue to accrete material slowly, still growing after millions of years, but showing little sign of ever achieving stellar ignition. Others have ceased their growth entirely, settling into a long, cooling phase that will last for billions of years. These stellar failures aren't truly failures at all, but represent an important component of galactic mass, contributing to the overall gravitational field and chemical evolution, even without nuclear burning. Their presence affects the efficiency of star formation in their parent clouds, competing for material that might otherwise go into forming more massive, successful stars. In studying these objects, astronomers gain insight into the complex physics of stellar birth and the conditions that determine whether a condensing gas cloud will become a shining star or a dim, failed remnant drifting through space. The approaching collision with our Milky Way will create tidal streams that stretch across millions of light years. As Andromeda draws closer to our galaxy over the next few billion years, the gravitational interaction between the two systems will begin to create spectacular tidal effects long before any direct collision occurs. Stars from both galaxies will be pulled into long, graceful streams that arc through space, creating bridges of starlight connecting the two systems. These tidal tails will stretch for millions of light years, visible from great distances as luminous threads marking the paths of gravitational interaction. The process will begin gently, with only the outermost stars affected at first, but will gradually intensify as the galaxies approach each other. Some stars will be completely ejected from both systems, flung into intergalactic space by the complex gravitational dance. Others will be captured and exchanged between the galaxies, creating mixed populations that blend the stellar contents of both systems. The tidal streams themselves will evolve over time, initially narrow and well-defined, but gradually dispersing as internal motions and external forces spread them out. These structures will persist for hundreds of millions of years, slowly fading as their constituent stars spread throughout the merged system. The streams will create some of the most beautiful large-scale structures in the local universe, temporary monuments to one of the most significant galactic encounters in cosmic history. Cosmic dust lanes within Andromeda create intricate shadow patterns that outline its spiral geometry. Threading through the galaxy's luminous arms are delicate traceries of dark material, cosmic dust clouds that absorb and scatter starlight to create complex patterns of shadow and illumination. These dust lanes aren't empty voids, but dense concentrations of microscopic particles, the remnants of stellar atmospheres and supernova explosions that have been shaped by magnetic fields and stellar winds into elegant filamentary structures. They follow the galaxy's spiral pattern with remarkable precision, outlining the density waves that maintain Andromeda's graceful form. The dust grains themselves are incredibly tiny, smaller than the wavelength of visible light, yet collectively they can obscure entire regions of the galaxy from view. In infrared wavelengths, these same regions glow warmly, heated by the radiation from nearby stars and revealing star formation activity hidden from optical telescopes. The dust lanes serve as cosmic highways for the raw materials of stellar birth. Inhaling gas and particles along the spiral arms, where they can accumulate and eventually collapse to form new stars. Their intricate patterns change slowly over millions of years as the galaxy rotates and evolves, creating an ever-shifting tapestry of light and shadow that adds depth and complexity to Andromeda's appearance. These dark threads weave through the galaxy like cosmic calligraphy, writing stories of stellar death and rebirth in patterns of shadow against the stars. Ancient white dwarf stars in Andromeda's halo tell tales of stellar generations that lived and died billions of years ago. Scattered throughout the galaxy's outer regions are the cooling remnants of stars that completed their life cycles when the universe was young, compact white dwarf stars that have been fading slowly for most of cosmic history. These stellar corpses are all that remain of an entire generation of suns that once illuminated the galaxy with their nuclear fires. Now they glow only with residual heat, gradually cooling toward the background temperature of space over timescales that exceed the current age of the universe. Some of these ancient white dwarfs are among the oldest objects in the galaxy, formed from stars that began shining just a few billion years after the Big Bang. Their surfaces preserve chemical signatures from that primordial epoch, when the galaxy contained far fewer heavy elements and stellar evolution proceeded under very different conditions. The white dwarfs drift silently through the halo on highly elliptical orbits that carry them far from the galaxy's plane, following paths established billions of years ago by the gravitational interactions that shaped Andromeda's early structure. Their faint light represents one of the galaxy's most persistent forms of stellar radiation, energy that will continue flowing into space long after all other stars have burned out and died. In their quiet glow lies the promise of cosmic longevity, reminders that even stellar death can create forms of beauty that endure across the ages. Hypervelocity stars, ejected from Andromeda's core, race through space at millions of miles per hour. Deep within the galaxy's central regions, gravitational encounters with the supermassive black hole occasionally accelerate stars to such extreme velocities that they escape the galaxy entirely, becoming cosmic refugees traveling at speeds that dwarf anything in our everyday experience. These stellar exiles were likely part of binary systems that ventured too close to the black hole's event horizon, where one star was captured while its companion was flung outward with tremendous force. Now they race through space at velocities exceeding 1,000 kilometers per second, fast enough to cross the entire galaxy in just a few 100 million years. Their trajectories carry them far beyond Andromeda's gravitational influence, into the empty spaces between galaxies where they will spend the rest of their lives in isolation. Some may eventually be captured by other galaxies they encounter during their long journey, while others will continue traveling through the cosmic void until the universe itself grows cold and dark. These hypervelocity stars carry with them the chemical heritage of Andromeda's core regions, spreading elements forged in the galaxy's heart throughout the local group. Their high-speed exodus represents one of the most dramatic ways that galaxies can exchange material, launching stellar ambassadors on journeys that span millions of light years and billions of years of time. Pulsating variable stars within Andromeda serve as cosmic lighthouses, their rhythmic brightening and dimming visible across millions of light years. Among the galaxy's stellar population are thousands of stars that change their brightness in regular cycles, swelling and contracting like vast stellar hearts, beating with periods ranging from hours to years. These variable stars include massive supergiants near the end of their lives, their outer layers so distended that they become unstable and pulsate with mechanical precision. Others are smaller stars in binary systems, where material flowing from one companion to another creates regular flares and eclipses that modulate the system's total light output. The most useful of these variables are the Cepheid stars, yellow supergiants whose pulsation periods are directly related to their intrinsic brightness, making them invaluable tools for measuring cosmic distances. Even from our distant vantage point, individual Cepheids in Andromeda can be observed and monitored, their light curves revealing not only their distances, but also details about stellar evolution and the galaxy's chemical composition. Some variables pulse so slowly that their cycles take years to complete, requiring decades of patient observation to understand their behavior fully. Others flash rapidly, changing noticeably from night to night as they cycle through their rhythmic variations. These stellar beacons create a kind of cosmic Morse code, their patterns of light and darkness carrying information about stellar physics across the vast gulf of intergalactic space. Vast molecular cloud complexes within Andromeda harbor the chemistry of future planetary systems. Hidden within the galaxy's spiral arms are enormous concentrations of cold gas and dust, molecular clouds that span hundreds of light years and contain the raw materials for millions of future stars and planets. These cosmic reservoirs are among the coldest places in the galaxy, with temperatures dropping to just a few degrees above absolute zero, conditions so frigid that hydrogen molecules can barely move. Within their dark interiors, complex chemistry unfolds at an almost impossibly slow pace, with atoms and molecules colliding and combining to form increasingly sophisticated compounds. The clouds contain not just simple hydrogen and helium, but also water vapor, carbon monoxide, ammonia, and even more complex organic molecules that could serve as the building blocks for life. Some regio, NS within these clouds, show signs of incipient collapse, areas where gravity is beginning to overcome the internal pressure and gather material into the dense cores that will eventually become new stars. The process of stellar birth will take millions of years to complete, but when it does, the new suns will inherit the chemical complexity of their parent clouds, potentially forming planetary systems rich in the heavy elements needed for rocky worlds. These molecular cloud complexes represent the galaxy's future potential, vast nurseries where the next generation of stars and planets will slowly take shape over cosmic timescales. Stellar streams from disrupted satellite galaxies create ghostly arcs that wrap around Andromeda's structure. The galaxy's gravitational influence has gradually torn apart numerous smaller companions over billions of years, spreading their stellar contents along graceful curved paths that trace their former orbits. These tidal streams appear as faint ribbons of stars when viewed with sensitive telescopes, their patterns revealing the complex dance of gravitational forces that shaped Andromeda's growth. Some streams are relatively young and well-defined, marking recent disruption events that scattered their parent galaxies across the sky within the last few 100 million years. Others are ancient and diffuse, their stars so widely spread that only statistical analysis can reveal their common origin. The streams follow the paths of least resistance through Andromeda's gravitational field, flowing like stellar rivers along invisible valleys in the local space-time geometry. Individual stars within these streams retain the chemical signatures of their birth galaxies, allowing astronomers to reconstruct the properties of systems that no longer exist as coherent entities. Over time, the streams will gradually disperse as their constituent stars spread throughout Andromeda's halo. But their patterns preserve the memory of ancient mergers long after the original galaxies have been completely absorbed. These ghostly arcs represent one of the most poetic aspects of galactic evolution. Beautiful remnants of cosmic encounters that transformed separate island universes into components of a single, larger system. Radio emissions from Andromeda reveal invisible structures powered by magnetic fields and high-energy particles. Beyond the wavelengths of visible light, the galaxy glows with radio radiation that traces entirely different phenomena from those we observe optically. These radio signals arise from high-energy electrons spiraling through magnetic fields, creating synchrotron radiation that illuminates structures invisible to ordinary telescopes. The radio emission reveals the galaxy's magnetic field architecture, showing how invisible force lines thread through the spiral arms and extend into the surrounding halo. Some of the strongest radio signals come from regions where supernova shock waves have accelerated particles to nearly the speed of light, creating cosmic ray populations that interact with magnetic fields to produce the observed radiation. Other radio sources mark the locations of neutron stars, rapidly spinning stellar remnants whose magnetic fields are so intense they accelerate particles and beam radio waves across space like cosmic lighthouses. The galaxy's overall radio emission creates a diffuse glow that extends far beyond its optical boundaries, revealing the presence of magnetic fields and energetic particles in regions that appear empty at other wavelengths. This radio architecture evolves slowly over time, as the galaxy's magnetic field is twisted by rotation and stirred by stellar activity, creating patterns that persist for millions of years before being disrupted by new sources of turbulence. Intermediate mass black holes may lurk within Andromeda's dense star clusters, representing a missing link in cosmic evolution. Scattered throughout the galaxy are massive star clusters that may harbor black holes with masses between those of stellar remnants and the supermassive giants found in galactic centers. These intermediate mass objects are among the most elusive phenomena in astronomy. too massive to form from single stellar collapse, yet too small to power the brilliant emissions associated with supermassive black holes. Within Andromeda's globular clusters, where hundreds of thousands of stars crowd into regions just a few light years across, the conditions may be right for such objects to form through the gradual merger of smaller black holes or the direct collapse of extremely massive stars. These hidden giants would reveal themselves only through their gravitational effects on nearby stars, creating subtle signatures in stellar motions that require careful analysis to detect. The presence of intermediate mass black holes would provide important clues about how supermassive black holes formed in the early universe, potentially representing evolutionary stepping stones between stellar mass and galactic scale objects. Their discovery would also help explain some puzzling aspects of globular cluster dynamics, such as the observed distributions of stellar velocities and the apparent ejection of stars from cluster cores. These cosmic missing links may be hiding in plain sight within Andromeda's stellar cities, invisible architects that help shape some of the galaxy's most ancient and stable stellar communities. The galaxy's rotation curve reveals the invisible scaffold of dark matter that holds everything together. As astronomers measure how fast stars orbit at different distances from Andromeda's center, they discover something puzzling that contradicts our expectations based on visible matter alone. In a normal system where mass is concentrated at the center, objects farther out should move more slowly, just as outer planets in our solar system take longer to orbit the Sun. But Andromeda's stars don't follow this pattern. Instead, they maintain roughly constant velocities even in the galaxy's outer regions, where visible matter is sparse. This flat rotation curve can only be explained by the presence of additional invisible mass, dark matter that extends far beyond the galaxy's luminous boundaries. The dark matter creates a vast spherical halo that may contain 10 times more mass than all the visible stars and gas combined, providing the gravitational scaffolding needed to hold the galaxy together and maintain its observed rotation pattern. This invisible architecture likely played a crucial role in Andromeda's formation, providing the gravitational framework around which ordinary matter could condense and organize into the spiral structure we observe today. The dark matter halo continues to influence the galaxy's evolution, affecting how it interacts with neighboring systems and how it will behave during its eventual collision with our own Milky Way. Stellar archaeology within Andromeda reveals the galaxy's complex assembly history through chemical fossil records. Like archaeological layers in ancient cities, the galaxy's stellar populations preserve chemical signatures that tell the story of its formation and evolution over cosmic time. The oldest stars, formed when Andromeda was young, contain mostly hydrogen and helium with trace amounts of heavier elements, reflecting the limited chemical inventory available in the early universe. Subsequent generations show progressively higher concentrations of carbon, oxygen, silicon, and iron, elements created and dispersed by earlier stellar deaths. But the chemical evolution wasn't uniform throughout the galaxy. Different regions show distinct patterns of enrichment, suggesting that Andromeda assembled through the merger of multiple smaller systems, each with its own star formation history and chemical heritage. Some stellar populations show unusual abundance patterns that don't fit the expected sequence of chemical evolution, indicating they formed in external galaxies before being incorporated into Andromeda through merger events. The chemical diversity preserved in the galaxy's stars creates a kind of fossil record, allowing astronomers to reconstruct the complex sequence of accretion events that built Andromeda into the massive spiral we observe today. Each chemical fingerprint represents a chapter in galactic history, a preserved memory of conditions that existed billions of years ago when the galaxy was still assembling itself from scattered fragments. Gravitational microlensing events within Andromeda occasionally reveal invisible objects through their distortion of background starlight. Sometimes, purely by chance, a dark object in the galaxy passes directly between a background star and Earth, creating a temporary brightening event as the intervening mass acts as a gravitational lens. These microlensing events are rare and brief, typically lasting only weeks or months, but they provide a unique window into populations of objects too faint to detect by any other means. The lensing can reveal brown dwarfs, isolated planets, stellar remnants, or even primordial black holes that would otherwise remain completely invisible. The precise shape of the brightness curve during these events encodes information about the lensing object's mass, stance, and motion, allowing astronomers to study dark matter components and exotic objects that make up the galaxy's hidden population. Some microlensing events show complex patterns that suggest the lensing object has companions, revealing binary systems or planetary systems that could never be detected through traditional methods. The technique is particularly sensitive to objects with masses similar to planets or small stars, filling in a crucial observational gap in our understanding of galactic mass functions. Each microlensing detection represents a cosmic coincidence, a chance alignment that briefly illuminates one of the galaxy's invisible inhabitants and adds another piece to the puzzle of what lurks unseen in the spaces between stars. Ancient supernova remnants continue to expand through Andromeda's interstellar medium millions of years after their initial explosions. Scattered throughout the galaxy's disk are the ghostly remains of stellar catastrophes that occurred long before human civilization existed. Expanding shells of hot gas and magnetic fields that mark the sites where massive stars ended their lives in spectacular fashion. These supernova remnants continue to grow slowly outward, sweeping up surrounding material and creating vast cavities in the interstellar medium that can persist for tens of millions of years. The shock waves from these ancient explosions heat the gas they encounter to millions of degrees, causing it to glow in X-ray wavelengths and creating some of the hottest regions in the galaxy. As the remnants age, they gradually slow down and cool off, but their effects on the local environment persist much longer. They create turbulence in the interstellar medium, stir magnetic fields, and compress nearby gas clouds in ways that can either trigger or suppress new episodes of star formation. The heavy elements created in the original stellar explosion continue to mix into the surrounding medium, enriching future generations of stars with the carbon, oxygen, and iron needed to form rocky planets. Some remnants eventually merge with others, creating vast interconnected networks of hot, low-density gas that can extend across hundreds of light years. These expanding monuments to stellar death play crucial roles in galactic ecology, regulating star formation and redistributing both matter and energy throughout Andromeda's structure. The galaxy's satellite system includes dozens of smaller companions, each with its own unique evolutionary history. Surrounding Andromeda like a family of cosmic children are numerous smaller galaxies, dwarf systems that orbit the giant spiral at various distances and follow their own distinct evolutionary paths. Some of these satellites are actively forming stars, their gas reserves still sufficient to fuel ongoing stellar birth despite their small sizes. Others have been stripped of their star-forming material by Andromeda's gravitational influence, and now consist entirely of aging stellar populations slowly fading toward invisibility. The satellite galaxies show remarkable diversity in their properties, ranging from compact elliptical systems dominated by ancient red stars to irregular dwarfs with active star formation regions glowing blue with young stellar light. Some maintain their structural integrity despite billions of years of tidal harassment from their massive host, while others are clearly being disrupted, their outer stars pulled away in long tidal streams. The orbital motions of these satellites provide important tests of gravitational physics and dark matter models, as their paths through space are determined by the combined gravitational influence of Andromeda's visible matter and invisible dark matter halo. Each satellite represents a successful survivor of galactic cannibalism, small systems that have managed to maintain their identity despite the overwhelming gravitational presence of their giant neighbor. Their continued existence adds richness and complexity to the Andromeda system, creating a dynamic environment where gravitational interactions continue to shape structure and evolution across cosmic time. Neutron stars within Andromeda spin with clockwork precision, some rotating hundreds of times per second. Among the galaxy's most exotic residents are neutron stars, the incredibly dense remnants of massive stellar explosions that have compressed the mass of our Sun into objects barely 20 kilometers across. These cosmic lighthouses emit beams of radiation that sweep across space as they rotate, creating pulsing signals that can be detected across millions of light years. Some of these stellar remnants spin so rapidly that they complete hundreds of rotations every second, their surfaces moving at significant fractions of the speed of light. The precision of their rotation rivals the best atomic clocks, maintaining timing accuracy that can persist for millions of years with minimal drift. This extraordinary stability makes them natural cosmic timepieces, their rhythmic pulses providing bench marks for studying gravitational physics and the behavior of matter under extreme conditions. The neutron stars formed from Andromeda's most massive stellar progenitors, stars that lived brief but brilliant lives before collapsing under their own gravity into these impossibly dense objects. Their magnetic fields are trillions of times stronger than Earth's, powerful enough to distort atomic structure and accelerate particles to tremendous energies. These spinning stellar corpses represent some of the most extreme physics laboratories in the universe, places where matter behaves in ways that cannot be replicated on Earth. Vast stellar associations within Andromeda create loosely bound groups that slowly disperse over millions of years. Not all stars form in tight, long-lasting clusters. Many emerge from star-forming regions as members of loose associations, gravitationally unbound groups that share common motion and chemical composition, but gradually drift apart as they orbit the galaxy. These stellar associations can span hundreds of light years and contain thousands of young stars, all born from the same giant molecular cloud, but lacking the gravitational cohesion needed to remain permanently together. Over time scales of tens of millions of years, the individual motions of member stars carry them away from their birthplace, spreading them throughout the galaxy's disk, while preserving subtle signatures of their common origin. The associations often contain the most massive and luminous stars in the galaxy, brilliant blue giants that illuminate vast regions of space during their brief lifetimes. These stellar monsters burn through their nuclear fuel so quickly that they explode as supernovas, while many of their lower mass siblings are still in the process of formation. The shock waves from these explosions can trigger additional rounds of star formation in nearby gas clouds, creating cascading episodes of stellar birth that propagate through entire spiral arms. By studying these dispersing associations, astronomers can trace the history of star formation in different regions of Andromeda and understand how stellar nurseries evolve from dense, active sites of stellar birth into the distributed stellar populations we observe today. Cosmic ray particles accelerated within Andromeda travel at nearly the speed of light, carrying energy across vast distances. Permeating all of space within the galaxy is a tenuous but persistent flux of high-energy particles, cosmic rays that have been accelerated to tremendous velocities by supernova shock waves, neutron star magnetospheres, and other extreme astrophysical phenomena. These subatomic bullets race through the galaxy at speeds approaching that of light, following complex paths as they interact with magnetic fields and encounter obstacles in their journey. Some cosmic rays are protons or heavier atomic nuclei stripped of their electrons and accelerated to energies millions of times greater than those achieved in the most powerful particle accelerators on Earth. Others are electrons or positrons that spiral along magnetic field lines, creating synchrotron radiation that contributes to the galaxy's radio emission. The cosmic ray population represents a significant reservoir of energy within Andromeda, comparable to energy stored in starlight, magnetic fields, and turbulent gas motions. These particles play important roles in heating the interstellar medium, driving chemical reactions in molecular clouds, and influencing the process of star formation. They also serve as probes of galactic structure, their interactions with matter and magnetic fields revealing information about conditions in regions too distant or too faint to study by other means. The cosmic ray flux varies throughout the galaxy, highest near sources of particle acceleration and lowest in regions shielded by dense gas clouds or strong magnetic fields. Planetary nebulae scattered throughout Andromeda mark the gentle deaths of sun-like stars with shells of glowing gas. When intermediate mass stars like our Sun reach the end of their nuclear burning phase, they don't explode violently like their more massive cousins, but instead shed their outer layers in a more gradual process that creates some of the most beautiful objects in the galaxy. These planetary nebulae, despite their name having nothing to do with planets, form intricate patterns of glowing gas illuminated by the hot central remnant of the original star. The expelled material expands slowly outward, creating shells, rings, and complex structures that can persist for tens of thousands of years before dispersing into the general interstellar medium. Each planetary nebula is unique, shaped by the specific conditions that existed during the star's final evolutionary phases, including rotation, magnetic fields, and the possible presence of binary companions. The glowing gases emit characteristic colors as atoms absorb ultraviolet radiation from the central white dwarf and re-emit it at specific wavelengths, creating a cosmic spectrum that reveals the chemical composition of the expelled material. These stellar death shrouds enrich the surrounding interstellar medium with heavy elements created during the star's lifetime, contributing carbon, nitrogen, and oxygen that will be incorporated into future generations of stars and planets. The central white dwarfs will continue to ionize their surrounding nebulae for thousands of years before gradually cooling and fading, leaving behind only the dispersing gas as evidence of their former stellar glory. Magnetic reconnection events within Andromeda's structure release tremendous bursts of energy through the sudden reconfiguration of field lines. Throughout the galaxy's magnetized plasma environment, magnetic field lines occasionally become twisted and stressed to the point where they suddenly snap and reconnect in explosive events that convert magnetic energy into kinetic energy and heat. These reconnection events can occur in a variety of environments, from the vicinity of neutron stars, where field strengths are extreme, to the more diffuse regions of the interstellar medium, where field lines from different sources interact. When reconnection occurs, it accelerates particles to high energies, heats plasma to millions of degrees, and can trigger shock waves that propagate through the surrounding medium. The process is similar to what happens during solar flares on the Sun, but scaled up to galactic proportions with correspondingly larger energy releases. Some reconnection events may be responsible for accelerating cosmic ray particles or creating the high-energy phenomena observed in various wavelengths of electromagnetic radiation. The magnetic field geometry within Andromeda is constantly evolving as the galaxy rotates and stellar activity stirs the magnetized plasma, creating ongoing opportunities for field lines to become tangled and eventually reconnect. These explosive reconfigurations represent one way that magnetic energy stored in galactic-scale structures can be suddenly released, contributing to the overall energy budget and dynamic behavior of the interstellar medium. Ancient collision scars preserved in Andromeda's stellar halo reveal the violent history of galactic assembly. The galaxy's outer regions contain subtle but persistent signatures of past merger events, imprinted in the positions, velocities, and chemical compositions of stars that once belonged to smaller galaxies before being incorporated into Andromeda's structure. These fossil records of cosmic cannibalism appear as kinematic substructure within the stellar halo, groups of stars that share common motion and chemical fingerprints, despite being scattered across vast regions of space. Some of these relics form coherent streams that can be traced for hundreds of thousands of light years, marking the orbital paths of disrupted satellites. Others appear as more diffuse overdensities or shell-like structures that represent different phases of the merger process. The chemical compositions of these accreted stars often differ from those born within Andromeda itself, reflecting the different star formation histories and environmental conditions that existed in their parent galaxies. By studying these ancient collision scars, astronomers can reconstruct the merger history of Andromeda and understand how massive galaxies like this one assembled themselves through the gradual accumulation of smaller systems. The process continues today on a smaller scale, as ongoing interactions with satellite galaxies add new material to the outer halo and create fresh disturbances in the stellar distribution. Each merger scar represents a chapter in galactic history, preserving the memory of independence. Indent stellar systems that sacrificed their individuality to become part of something larger. Circumgalactic medium surrounding Andromeda extends far beyond the visible galaxy, creating a vast reservoir of hot, diffuse gas. Enveloping the entire visible structure of Andromeda is an enormous atmosphere of hot, tenuous gas that extends for millions of light years in all directions, far beyond the reach of the spiral arms and stellar halo. This circumgalactic medium represents a significant fraction of the galaxy's total baryonic mass, yet it remains largely invisible except when observed in ultraviolet and X-ray wavelengths. The gas exists at temperatures of millions of degrees, heated by supernova explosions, stellar winds, and gravitational processes associated with the galaxy's formation and evolution. This hot halo serves as both a reservoir and a conduit, storing gas that may eventually cool and fall back into the galaxy to fuel future star formation, while also providing a pathway for material ejected by stellar activity to escape into intergalactic space. The circumgalactic medium plays crucial roles in regulating the galaxy's star formation rate and chemical evolution, controlling the flow of gas into and out of the stellar disk. Its properties vary with distance from the galaxy center and show signs of rotation and other organized motions that reflect the underlying gravitational potential. Interactions with satellite galaxies and the infall of material from the cosmic web create disturbances in this hot atmosphere that can persist for hundreds of millions of years. The medium also contains significant amounts of heavy elements, metals created by stellar nucleosynthesis and dispersed through supernova-driven winds that carry enriched material far from its stellar sources. Stellar streams from globular cluster disruption create faint trails that trace ancient orbital paths through the galaxy. Even the most tightly bound stellar systems in Andromeda occasionally succumb to the relentless tidal forces exerted by the galaxy's gravitational field, particularly when their orbits carry them through regions of high stellar density or close to the central black hole. When globular clusters are disrupted, their constituent stars don't simply disperse randomly, but instead follow the cluster's original orbital path, creating narrow streams of stars that can extend for tens of thousands of light years along graceful curves through the galactic halo. These tidal streams are incredibly faint, containing stars that were once gravitationally bound together, but now drift independently along parallel trajectories. The streams evolve slowly over time as differential gravitational forces gradually spread the stars along their common orbit, but the basic structure can persist for hundreds of millions of years. Some streams show evidence of multiple wraps around the galaxy, indicating that their parent clusters survived many orbital periods before finally being torn apart. The discovery and study of these streams provides important constraints on the galaxy's gravitational potential and the distribution of dark matter within its halo. Each stream represents the death of an ancient stellar city, a globular cluster that may have survived for most of the galaxy's history before finally succumbing to the tidal forces that govern galactic dynamics. The stars within these streams carry with them the chemical signatures of their former cluster environment, preserving information about stellar nucleosynthesis processes that operated in dense stellar systems billions of years ago. Supermassive black hole activity in Andromeda's center occasionally creates brief flares visible across electromagnetic wavelengths. While the galaxy's central black hole typically remains relatively quiet, occasionally material falls toward it in ways that create sudden increases in radiation output across multiple wavelengths simultaneously. These flaring events can brighten the galactic nucleus by factors of hundreds or thousands, creating temporary beacons that outshine millions of ordinary stars before fading back to quiescence over periods ranging from hours to months. The flares result from the disruption of gas clouds, stellar atmospheres, or possibly entire stars that venture too close to the black hole's event horizon, where tidal forces stretch and heat the material to tremendous temperatures. As the disrupted matter spirals inward, it forms an accretion disk that glows brilliantly in ultraviolet and X-ray radiation, while also producing radio emission from jets of particles accelerated to near light speed. The timing and intensity of these flares provide important clues about the physical processes operating near the black hole and the properties of the surrounding environment. Some flares may be triggered by the interactions between the black hole and binary star systems, while others might result from the infall of molecular clouds or debris from stellar collisions. The unpredictable nature of these events makes them challenging to study systematically. But when they do occur, they offer rare opportunities to probe the immediate vicinity of one of the most extreme gravitational environments in the local universe. Binary evolution within Andromeda's dense stellar environments creates exotic stellar remnants through mass transfer processes. In regions where stars are crowded closely together, particularly within globular clusters and the galaxy's central bulge, stellar evolution can follow very different paths than it does for isolated stars like our Sun. When two stars orbit closely enough that their outer layers begin to interact, complex mass transfer processes can dramatically alter their evolutionary trajectories, creating objects that would be impossible to form in isolation. Some binaries undergo episodes where material flows from one star to its companion, rejuvenating the receiving star and potentially extending its main sequence lifetime far beyond what would normally be expected. Other systems experience more violent interactions, including stellar mergers that create unusually massive stars or exotic objects like blue stragglers that appear younger than their surroundings despite forming from ancient stellar populations. The most extreme binary interactions can lead to thermonuclear explosions when white dwarf stars accrete enough material from their companions to exceed critical mass thresholds, creating Type 1 supernovas that briefly outshine the entire galaxy. Some binary systems produce millisecond pulsars, rapidly spinning neutron stars that have been spun up through accretion from their companions. while others create unusual chemical abundance patterns that reflect the complex nucleosynthesis processes operating in interacting stellar atmospheres. The dense stellar environments within Andromeda provide natural laboratories for studying these exotic evolutionary pathways, revealing the full range of possible outcomes when stellar evolution proceeds under the influence of close gravitational companions. Galactic fountain processes within Andromeda cycle material between the disk and halo through supernova-driven outflows. The galaxy's star-forming regions don't simply convert gas into stars in a one-way process, but instead participate in a complex circulation system that moves material vertically through the galactic structure over timescales of hundreds of millions of years. When massive stars explode as supernovas, their combined energy can drive powerful winds that lift gas from the disk into the surrounding halo, creating plumes of hot material that rise far above the plane of the galaxy. This ejected material doesn't escape entirely, but instead cools and condenses as it reaches the maximum height of its trajectory, eventually falling back toward the disk under the influence of the galaxy's gravitational field. The falling gas carries with it heavy elements created by stellar nucleosynthesis, helping to enrich the interstellar medium with the carbon, oxygen, and iron needed for planet formation. This galactic fountain process helps regulate star formation rates by removing gas from active star-forming regions, while simultaneously providing a mechanism for redistributing metals throughout the galaxy's structure. The circulation timescales are long enough that individual parcels of gas may complete several fountain cycles during the galaxy's evolution, gradually becoming more enriched with heavy elements with each passage through stellar processing regions. The fountain also creates a kind of galactic weather system, with hot gas rising from the disk and cooler material raining back down in a cycle that has continued for billions of years and will likely persist as long as star formation continues within the galaxy's spiral arms. Dark matter subhalos within Andromeda create invisible gravitational scaffolding that influences visible matter in subtle ways. Throughout the galaxy's vast dark matter, halo exist countless smaller concentrations, subhalos that formed during the early universe and were later incorporated into Andromeda's gravitational embrace. These dark matter clumps are completely invisible, containing no stars or gas of their own, yet their gravitational influence can be detected through careful analysis of stellar motions and gas dynamics in their vicinity. Some subhalos may have masses equivalent to millions of suns despite being utterly dark, creating gravitational disturbances that affect the orbits of nearby stars and the flow of interstellar gas. The largest of these subhalos might once have hosted their own small galaxies before being stripped of their visible matter through tidal interactions with Andromeda's main structure. Now they drift through the galaxy like gravitational ghosts, their presence revealed only by the subtle ways they bend space and influence the motion of visible matter. The distribution and properties of these dark subhalos provide important tests of cosmological models and our understanding of how structure formed in the early universe. They represent the fundamental building blocks from which larger structures like Andromeda assembled themselves, invisible foundations that continue to shape galactic evolution long after their incorporation into the main system. Stellar kinematics within Andromeda reveal complex patterns of motion that preserve the memory of ancient formation processes. The velocities of stars throughout the galaxy don't follow simple, predictable patterns, but instead show intricate variations that reflect the complex history of galactic assembly and evolution. Stars in different regions move at different speeds and in different directions, creating a three-dimensional velocity field that encodes information about past merger events, ongoing gravitational interactions, and the underlying mass distribution of both visible and dark matter. Some stellar populations show organized streaming motions that suggest they originated elsewhere and were later accreted into Andromeda's structure, while others display the random velocity dispersions expected from stars that formed within the galaxy itself. The oldest stellar populations typically show the most complex kinematic patterns, reflecting the chaotic conditions that existed during the galaxy's early assembly phase. Younger stars generally follow more ordered motions, particularly in the disk, where they participate in the galaxy's overall rotation, while also showing smaller-scale streaming patterns associated with spiral arm dynamics. These velocity patterns change slowly over cosmic time as gravitational interactions gradually mix different stellar populations and erase the signatures of ancient formation events. By studying stellar kinematics in detail, astronomers can reconstruct aspects of Andromeda's formation history that are otherwise lost to time, reading the galaxy's past in the present-day motions of its stellar constituents. Interstellar turbulence within Andromeda creates cascading energy flows that influence star formation across multiple scales. The gas between stars is far from static, but instead exhibits complex, turbulent motions that span enormous ranges of size and timescale. From molecular cloud cores just a few light-years across to galactic scale flows that encompass the entire spiral structure. This turbulence is driven by multiple sources of energy injection, including supernova explosions, stellar winds, gravitational instabilities, and the galaxy's differential rotation, creating a dynamic environment where gas motions are never truly at rest. The turbulent energy cascades from large scales to smaller ones through a hierarchy of eddies and vortices, much like atmospheric turbulence on Earth, but operating in the near-vacuum conditions of interstellar space. This turbulent motion provides support against gravitational collapse in molecular clouds, regulating the efficiency of star formation and determining where and when new stars will form. At the same time, turbulence can also trigger star formation by compressing gas in shock waves and creating density fluctuations that become gravitationally unstable. The interplay between turbulent support and gravitational collapse creates a complex, non-linear system where small changes in initial conditions can lead to dramatically different outcomes for star formation. Understanding this turbulent cascade is crucial for predicting how galaxies like Andromeda will evolve over cosmic time. As turbulence helps determine the rate at which gas is converted into stars and the efficiency with which heavy elements are mixed throughout the interstellar medium. Tidal heating processes within Andromeda's satellite system create internal energy sources that can drive continued evolution. The gravitational forces exerted by the massive galaxy on its smaller companions don't simply pull them inward, but also create internal stresses that generate heat through friction and deformation within the satellite structures. This tidal heating is most pronounced for satellites on highly elliptical orbits that experience varying gravitational forces as they move closer to and farther from Andromeda's center, causing them to be alternately stretched and compressed in a process that converts orbital energy into internal heat. The heating effects can maintain elevated temperatures within satellite galaxies long after their initial formation, potentially extending periods of star formation or creating unusual thermal structures that wouldn't exist in isolated systems. Some satellites may experience tidal heating strong enough to drive gas outflows that strip away their star-forming material, while others might have their internal dynamics altered in ways that affect stellar evolution or the formation of compact remnants. The process operates on long timescales, with individual heating episodes corresponding to orbital periods that can span hundreds of millions of years, but the cumulative effects can be substantial over cosmic time. Tidal heating also creates feedback mechanisms that can alter satellite orbits. ES mass loss, driven by internal heating, reduces gravitational binding and allows satellites to drift to larger distances where tidal forces are weaker. These complex interactions between orbital dynamics and internal evolution make satellite systems like Andromeda's natural laboratories for studying gravitational physics and stellar evolution under extreme conditions. Galactic archaeology within Andromeda uses stellar populations as fossil records to reconstruct billion-year-old formation events. Each generation of stars within the galaxy preserves chemical and kinematic signatures from the time and place of their birth, creating a kind of geological record written in starlight that can be decoded to reveal the galaxy's assembly history. The oldest stellar populations contain stars with chemical compositions that reflect the conditions existing when the universe was young and heavy element production was just beginning, while more recent generations show the progressive enrichment that has occurred through billions of years of stellar evolution. Different stellar populations also preserve kinematic information about the gravitational environment in which they formed, with velocity patterns that can reveal whether they originated within Andromeda itself or were accreted from smaller galaxies that have since been disrupted and absorbed. By carefully analyzing the properties of stellar populations at different locations throughout the galaxy, astronomers can identify groups of stars that share common origins and trace their connections back to specific formation events that occurred billions of years ago. Some stellar populations show chemical abundance patterns that suggest they formed during intense episodes of star formation triggered by galaxy mergers, while others display the more gradual enrichment expected from steady stellar evolution within an undisturbed system. This stellar archaeology reveals that Andromeda's current structure results from a complex history of accretion events, internal evolution, and gravitational interactions that have continued throughout cosmic time, with each stellar population contributing its own chapter to the galaxy's ongoing story. Magnetic dynamo processes within Andromeda generate and maintain galactic-scale magnetic fields through the conversion of kinetic energy. The galaxy's rotation and internal motions create conditions conducive to dynamo action, where the movement of electrically conducting plasma generates magnetic fields that can grow and persist over cosmic timescales. This process operates through the complex interplay between differential rotation, which stretches and amplifies existing magnetic field lines, and turbulent motions that twist and fold the field in ways that can regenerate it against the natural tendency toward decay. The dynamo mechanism requires a delicate balance between field generation and dissipation, with the galaxy's rotation providing the energy source, while turbulence and other forms of plasma instability create the complex field geometries needed for sustained dynamo action. Different regions of the galaxy may support different types of dynamo processes, with the disk exhibiting organized field patterns that follow the spiral structure, while the halo shows more chaotic field configurations that reflect the turbulent motions of hot gas in those regions. The magnetic field strength and geometry evolve slowly over time as the galaxy's rotation pattern changes and stellar activity injects new sources into the system of turbulence, creating a dynamic magnetic environment that influences many aspects of galactic evolution. The dynamo-generated magnetic fields play important roles in regulating star formation, guiding the propagation of cosmic rays, and affecting the dynamics of the interstellar medium, making them integral components of the galaxy's overall structure and evolution. Accretion processes around Andromeda's central black hole create temporary storage structures that can persist for millions of years before final consumption. Material that falls toward the galaxy's supermassive black hole doesn't always plunge directly past the event horizon, but can instead settle into orbiting configurations that allow it to spiral inward gradually over extended periods. These accretion structures can take various forms, from hot, geometrically thick flows where thermal pressure provides support against gravitational collapse to thin, cold disks where angular momentum transport through magnetic and gravitational torques determines the infall rate. The properties of the accretion flow depend critically on the rate at which material is supplied to the black hole region and the physical conditions of that material when it arrives. With different accretion modes, producing very different observational signatures and evolutionary timescales. During periods of enhanced accretion, the material can heat up sufficiently to produce significant electromagnetic radiation, creating temporary episodes of increased luminosity that can be detected across multiple wavelengths. The accretion process also generates powerful outflows and jets that carry energy and momentum away from the black hole region, potentially affecting star formation and gas dynamics throughout the galaxy's central regions. These feedback mechanisms create complex interactions between the black hole and its host galaxy, with accretion episodes influencing galactic evolution, while the galaxy's properties determine the supply of material available for future accretion events. Chemical gradients within Andromeda's disk reflect the inside-out formation process and ongoing stellar nucleosynthesis. The abundance of heavy elements doesn't remain constant throughout the galaxy, but instead shows systematic variations with distance from the center, creating chemical gradients that provide important clues about how the galaxy formed and evolved over cosmic time. Stars in the inner regions typically show higher concentrations of elements like oxygen, carbon, and iron compared to their counterparts in the outer spiral arms, reflecting both the more intensive star formation activity that has occurred in the central regions and the longer timescales available for chemical enrichment in those areas. These gradients suggest that galaxy formation proceeded from the inside out, with the central regions assembling first and achieving higher levels of chemical enrichment, before star formation extended into the outer disk regions. The gradients are maintained by the relatively slow mixing timescales that characterize galactic evolution, with radial transport of material proceeding slowly enough that chemical differences established during early formation epochs can persist for billions of years. However, the gradients do evolve gradually as ongoing stellar evolution continues to enrich the interstellar medium, and various transport processes slowly redistribute heavy elements throughout the galactic structure. Supernova explosions, stellar winds, and gas flows associated with spiral arm dynamics all contribute to the slow process of chemical mixing that will eventually flatten the abundance gradients over cosmic time. The current chemical structure of Andromeda's disk thus represents a snapshot of an ongoing process that began with galaxy formation and will continue as long as star formation persists within the galactic structure. Resonance phenomena within Andromeda's gravitational field create stable orbital configurations that trap stars and gas for billions of years. The galaxy's gravitational potential isn't uniform, but contains regions where orbital frequencies match in ways that create long-lasting resonant relationships between different components of the galactic structure. These resonances can occur between stellar orbits and the rotation of spiral density waves, between different orbital frequencies within individual stellar orbits, or between the motions of gas clouds and the underlying gravitational field variations. Stars trapped in resonant configurations tend to maintain stable orbital relationships over very long timescales, creating persistent patterns in the stellar distribution that can influence the galaxy's overall structure and evolution. Some resonances act to confine material within specific radial ranges, helping to maintain the sharp boundaries observed between different galactic components, like the disk and halo, while others create gaps or underdense regions where resonant interactions prevent stable orbit formation. The spiral arms themselves may represent manifestations of resonant phenomena, with density waves propagating at speeds that maintain resonant relationships with stellar orbits at specific galactic radii. Gas dynamics can also be strongly influenced by resonant effects. Shock waves forming at resonance locations, where gas flow patterns interact with the underlying gravitational field structure. These resonant phenomena evolve slowly as the galaxy's mass distribution changes through stellar evolution and accretion of new material, creating a dynamically evolving system where resonance locations shift gradually over cosmic time, while continuing to play important roles in maintaining galactic structure and regulating the flow of material through different regions of the system. Stellar evolution pathways within Andromeda's dense environments produce exotic objects through non-standard evolutionary channels. In regions where stellar densities are extremely high, such as the cores of globular clusters or the immediate vicinity of the central black hole, stellar evolution can proceed along pathways that are impossible in the isolated conditions where most stars spend their lives. Close gravitational encounters between stars can alter their internal structure, strip away outer layers, or trigger enhanced nuclear burning that accelerates evolutionary timescales dramatically. Some stars may experience direct collisions with their neighbors, creating merged objects with unusual mass distributions and chemical compositions that reflect the violent circumstances of their formation. Binary evolution in dense environments can produce exotic systems where mass transfer processes operate under extreme conditions, potentially creating objects like helium stars, carbon white dwarfs with unusual masses, or neutron stars with properties that differ significantly from those formed through standard single-star evolution. The high-velocity dispersions characteristic of dense stellar systems can also lead to unusual outcomes when binary systems are disrupted through gravitational interactions, creating single stars with chemical abundance patterns that preserve evidence of their former binary nature. These alternative evolutionary pathways contribute to the diversity of stellar populations observed within Andromeda and provide natural laboratories for studying stellar physics under extreme conditions that cannot be replicated in less dense galactic environments. The exotic objects produced through these processes may persist for billions of years after their formation, serving as fossil evidence of the extreme conditions that existed during earlier phases of galactic evolution when stellar densities were higher and gravitational interactions more frequent. And now, as our gentle journey through Andromeda draws to a close, perhaps your thoughts have grown softer, your breathing deeper, your mind drifting like starlight across the vast distances we've traveled together tonight. We've wandered through spiral arms older than Earth itself, past stellar nurseries where future suns are taking shape in the cold darkness, and through the invisible rivers of dark matter that hold this magnificent galaxy in their silent embrace. In every fact we've shared, in every cosmic process we've explored, there lies a reminder that the universe is both impossibly vast and intimately connected to the quiet moment you're experiencing right now. The trillion stars of Andromeda continue their ancient dance. The galactic fountain keeps cycling material between disk and halo, and somewhere in those distant spiral arms, new worlds may be forming under alien skies. But for now, let these gentle truths settle around you like cosmic dust, and may your dreams tonight be filled with the patient turning of spiral arms, the soft glow of stellar nurseries, and the quiet promise that 4 billion years from now, when Andromeda finally embraces our Milky Way, it will create something even more beautiful than what exists today. Sleep well, and thank you for drifting through the cosmos with us.